Cool. So let's go ahead and jump right in. So yesterday we left off here talking about tangent planes. We also called them affine or linear approximations. Okay. And this here is why we call them linear approximations, because this formula here, while it's the equation for a plane, you can also view it as kind of an approximation. Z is approximating this function x, comma y, if xy is close to x sub 0, y sub 0, or x naught, y naught. So you can think that this is f of x sub 0, y sub 0, plus a little bit and plus a little bit of extra stuff. So this is like the what we'd call like the error term for, this is, of course, if you move away from x sub 0, y sub 0, then this is going to be, we're only going to, f is not going to change very much if f is a smooth function, is a differentiable function. Then f is not going to change very much. And this is kind of quantifying, hey, it's probably only going to change by approximately this much. And so this is kind of how you can view this as an approximation. We'll see a good example of that in a couple of slides. But first, let's jump into let's just compute some tangent planes to get comfortable with that, or compute a tangent plane to get comfortable with that. So here we have a point, or here we have a function. Okay, it's this function f of xy is equal to 4 minus x squared minus y squared. And we're looking at the tangent plane at 2, 0. And if we double check here, we plug in 2, 0, the z value is going to be 0 as well. So technically we're looking at 2, 0, 0, and we're looking at the tangent plane at that point. So, right, because when we call it the tangent plane, we're actually looking at the tangent plane of the graph. And the graph of a function from 2 dimensions to 1 dimension, right? This is a scalar valued function in 2 variables. So scalar valued function in 2 variables, the graph of that would live in 3 dimensions. So I need a 3-dimensional point on the plane, and then I need to figure all that out. But let's just go ahead and jump into using our formula. So we have basically this is our f here, of course, and then this is x naught, y naught right here. And so that there, we're going to use that to fill in this formula that I've boxed here. So let's start by just taking the partial derivatives. So df dx, right? This is going to be dx is going to be, or with respect to x, this term, the 4 and the minus y squared do not change with respect to x, and so their derivatives are 0. But then the negative x squared becomes negative 2x, and then df dy, something similar happens, except this 4 minus x squared is not changing with respect to y, so that goes to 0, and then the negative y squared becomes negative 2y. Okay, so we knew we were going to have to take the partials to compute a tangent plane. You're always going to have to take the partials. But let's look what else we need. So we have the partials, but then we have to plug in the actual point we're talking about. So let's go ahead and do that. So we're going to plug in, so at 2, 0, again, at 2, 0. That's because we want an actual number to come out. We don't want anything with x's and y's, right? We want a plane. So if you look at this here, right, this whole thing here should be a number, and this whole thing here should be a number. These should be numbers right here. So we need to plug in values for x and y. In this case, you plug in 2 for x and 0 for y. So df dx at 2, 0 is equal to negative 4, and df dx or dy at 2, 0 is 0. Okay. Cool. So now we have this information here, and we can plug that back into the formula here, and we get z is equal to, actually we need one more piece of information, right? We need f of x sub 0, y sub 0. So we're going to compute that over here, f of 2, 0, right? Because x sub 0, y sub 0 is 0, is equal to 4 minus 2 squared minus 0 squared, which I think I mentioned this out loud earlier, but it's good to see it in writing. This is 0. So we actually get a 0 out of here. A lot of zeros in this one, so the end result's going to be simpler. But in general, you might get like numbers here, and so your end result you might have more terms left over than I will. But you get 0 plus negative 4 times x minus 2 plus 0 times y minus 0. Right, so this is me just straight up plugging into that formula on the previous slide. Now I can totally simplify this, and this gives me z is equal to negative 4x plus 8. Okay, and that there's our formula. Any questions on that? Computations aren't too hard, so. One thing I did want to show real quick, just for just for the sake of kind of visualizing what's going on, I pulled up GeoGebra here. Sorry, I should have prepped that. GeoGebra, and I'm just going to go ahead and pull that up here. There it is. Okay, does everyone see GeoGebra now, the 3D calculator here? Should have changed screens. Cool. Okay. So this is my 3D plane. So what I'm going to do is I'm going to graph both of those. Okay, now it's stuck in this. Oh, there you go. Okay. So be hard to control sometimes. Cool. Okay, so let's go ahead and plot those functions. So the function was x comma f of x comma y was equal to 4 minus x squared minus y squared, right? So we get this here, which is, if you remember the other day when I was talking about some 3D shapes, the name of this is called a paraboloid, right? That's the type of shape this is. And the tangent plane we computed was z equals negative 4x plus 8. Okay. And what I'm going to do here is just change this color. Can I change that color? It's a little, just so that it's a little easier to see. So maybe greenish color. Maybe one like that. Okay. And what we can see if we rotate around is that right at this point here, which you can see is 2, 0, 0, right? Right at this point, this plane is just sitting tangent to this shape here. So all that computation showed us that this tangent plane here is tangent to this shape at that point, 2, 0, 0. Okay. Cool. So, oops. Any questions about that? Yeah, so this is a good way to visualize things. Good tool for that if you're struggling with a certain problem. Okay, cool. Let's switch back to my notes. Okay. Cool, and we'll move on to the next problem. Okay, so this is if you need to find the equation for a tangent line, but what if we want to actually use this as some kind of approximation? So I called the tangent plane, I said it's also called the linear approximation of the function, or affine approximation. And the whole point of that is to be able to estimate certain functions. So you see here, we're going to use linear approximation to estimate this value here, which is like kind of a scary looking value, 2.01 e to the 1.99. So let's see how we would go about doing this. So what we want to notice is that these numbers are actually really close to some nice numbers, right? 2.01 is really close to 2. 1.99 is really close, is also really close to 2, right? So we can, the fact that they're close to the same number doesn't matter. Like if this was 2.01 and this was 3.99, and that would still be fine, right? The point is that they're close to, they're both close to numbers. Someone's raising their hand. Does someone have a question? Okay, so let's jump into this problem here then. Okay, so the way we're going to do this is we're going to basically cook up a function that we can use to estimate this guy. So the function is going to be in two variables, right? Because we're noticing that there's two values here that we're going to use to approximate, right? And so it's going to be, we're going to say this is x e to the y, okay? And now maybe you want to write y e to the x, that's totally fine too. Okay. And then the other thing we're going to do is we're going to let x naught comma y naught be the points that are close to this. So since x was the thing out front, this is going to be 2, 2, right? Again, if they were different, if they were close to different numbers, then this would be whatever x is close to, and this would be whatever y is close to. Okay, so we're going to use this nice point to estimate this less nice point here. Okay, so what we can say is that f of x comma y is approximately, right? So I'm going to go back a couple of slides just to point something out, and I'll come back to this slide. We said that f of x comma y is approximately z near this point. And so we're going to use this formula to approximate f of xy. So f of xy is approximately f of 2, or I should be even more precise. Instead of saying f of xy, I should say the thing I'm trying to compute, is f of 2.01 comma 1.99. This is the thing I'm trying to compute. And this is approximately f of 2 comma 2, right? So far this makes sense, right? We only changed the number 2 and the numbers 2 and 2 by a little bit on each coordinate. So it's going to be pretty close to this number, but we have to add in some error terms. And the error terms here are going to be the partial of f with respect to x plugged in at 2 comma 2. And then here we're going to have 2.01 minus 2. And then we're going to add to this the partial of f with respect to y plugged in at 2, 2. And then here we're going to have 1.99 minus 2. Okay, so what we've done here is we've taken the formula for the tangent plane and used it to approximate a specific value of this function. So we introduced this function just to be able to use the linear approximation. And we said we're trying to compute this function evaluated at this kind of wacky point. And we're going to use this sort of, we're going to use the nice point as like a jumping off point, and then we're going to add on some error terms based on linear approximation. So how does this simplify? So f of 2 is 2e squared. And now we need to compute the derivatives, the partial derivatives of f with respect to x. So with respect to both variables. So the partial with respect to x is just, if we look at it here, it's just e to the y, right? And the partial with respect to y is x e to the y, right? Remember, e to the y, the derivative of e to the y is just e to the y. Okay, and so then we'll plug in 2 when we get there. So here, this is e squared times 2.01 minus 2 is 0.01. That should be 0.01. And then 2 is going to be 2e squared, and then we have negative 0.01. Okay. We could simplify this by factoring out the e squared out of all of this, and then we get 2 plus 0.01 minus 0.02. Let me make sure I got that right. Yeah. Someone's asking, where did I get the e squareds from? So here, this e squared is just this derivative df dx, right? Evaluated at 2, 2. I have to plug in 2 and 2 for x and y. So the y here becomes a 2. And then here, this is similar, 2e to the 2. 2e to the 2. So that's how I get all these x squareds. Because when for tangent planes and for linear or linear approximations, this you actually have to plug in that point. So then here this simplifies to 1.99 e squared. The idea here being that e squared is a much nicer thing to compute than e to the 1.99. And so we've estimated this in terms of something that's slightly nicer. Though there's still this 1.99 hanging around. So still not super nice, but it's nicer than what we started with. Okay, cool. Any questions? Someone's asking, for x0 and y0, we must assume the nearest number. Yeah, so the whole point of this is that we're going to use this, we're going to use nice numbers here. So just, these are usually going to be close to some whole number for the problems we give you, because whole numbers tend to be nicer. And we're going to say, okay, just go to some whole number, and we get, we can approximate this by just plugging in the whole number. Okay. So you can imagine maybe, you know, something with like if there was like trig involved, maybe the nice number would be like something involving pi or something. So if it's, someone said if it's 2.5, do we assume 2, 3, or 2? If it's 2.5, that's like, you can probably, it's gonna be equally good if you do either of them. Basically, it's like, it's, you know, you can go either 2, 3, or 2. Usually with these problems, they give you something that looks like this. It's like, it's very clear which way you should go. It's like, it's usually like a 100th away from a nice number. Would it be different if we used y e to the x? Basically, this term and this term would just be swapped. You'd get the same answer, but these terms would be swapped. Because you'd take the partial with respect to the other one and get the other answer, et cetera, et cetera. Okay. Good questions. Other questions? Okay. Yeah, so there's a couple of these on the homework. Go ahead and like take a look at those and try them out. Hopefully this gives you a good starting, like a good way forward for those types of problems. You know, if you like to memorize things, you can just memorize that formula, that plain formula, and just kind of this, just all it is an application of that formula. But if you like to, you know, understand things a little more deeply, then you can kind of start to pick apart why exactly this happens. So like, for example, like if you just ignore these extra terms, I think it's not hard to see that if I'm plugging in these numbers, that's going to be really close to just plugging in 2, 2, right? And then this stuff is just your error terms, and it's like it's your change in f of x, or your change in x, right? Your rate of change with respect to x, minus how much x has actually changed, and then your rate of change with respect to y minus how much y has actually changed, right? So that's kind of what we have going on here. Okay, cool. Cool. So let me move on to some more stuff. I don't want to run out of time here again. So the next page here, we're talking about the total, something called the total derivative. So we talked about partial derivatives. What the total derivatives are is basically so like a partial derivative was for single or scalar valued functions in several variables. But what a total derivative you can talk about for, something arbitrary. And what it is it's kind of just putting all of the derivatives together. And the way we do that is you take the matrix, you put all of the possible partial derivatives into a matrix is basically what it is. So df1, dx1, df1, dxn, df1, fm, dx1, df m, dxn. So what is f1 through fm? So remember, we can take a function and we can write the output, instead of writing it as, we can think of the output as a vector. I think I'm going to use just the x notation. We can think of it as it has a vector valued output, and so we can just think of the output as just a bunch of scalar valued functions. So this is just saying break up f into its scalar valued parts, which was a trick we used in the last section too. Basically, you can say like, okay, just look at the scalar valued parts and then just take the partial derivatives of each of these in every possible combination. So this is every possible combination of partial derivatives you can take. And the notation for this is the df. Okay, capital D F. Yeah, so it's like partial derivatives is this little squiggly d. This is like all of them, so it's the big capital D of f. So the computations of this is just like do every possible partial derivative. You should keep track of which kind of which one are the rows and which ones are the columns. You might end up kind of flipping this if you're not careful. Okay. And then there's one special case of for the total derivative. That's what's going to be on the next slide. I'm just giving you guys a second to get this copied down. So if you take in particular a scalar valued function, so here in the case where m equals 1, this is a scalar valued function, then the gradient of f is just we'd call the total derivative the gradient of f. Okay, so sometimes instead of writing capital D for the gradient specifically, when we have a scalar valued function, we use this upside down triangle, and that's called the gradient of f. I think the actual symbol itself is called a nabla, but I usually just refer to it as the gradient of f. And so this will look like a vector because it's just, or you could think of it as a row matrix. Either way you want to think about it, but this is just df dx1 all the way to df dxn. Should be a 1 there. Right. So you could think of it as a vector, or you could think of it as a row matrix if you're thinking of this, the total derivative. Okay. again, this is just the total derivative and the gradient are both just a way of putting together all of the information about the derivative, right? And so it's this list of partial derivatives, and so you can have every possible partial derivative there. Okay, and it'll get you this. It turns out that this vector is actually pretty useful to this function. We'll see that in some of the next few sections. Okay, cool. Okay, any questions about any of this? They're not crazy. I just wanted to make sure that we introduce. It's more like a vocab thing, like if we start talking about the total derivative, or also I should mention the total derivative. So I think in a textbook is referred to as the matrix of partial derivatives. So sometimes it's called that instead of total derivative. Okay. Cool. Okay. So that's it for this section. We're going to move on to the next section. We do jump, it is jumping around a little bit. So we're going to move to to chapter 3 next, just for one section. And then we're going to come back to chapter 2 next week. So we're in the middle of chapter 2. We're going to take a break, go do the first section from chapter 3, and then jump back and finish off chapter 2. But I think this is a natural place to take a break. Okay, welcome back. Nice little break. Let's, go ahead and switch gears to the next chapter, or the next section, which is from the next chapter, but then we'll come back to chapter 2 to finish it off next week. So it is skipping around a little bit, just because I think this is a good place to insert this section. But we will come back to the rest of chapter 2. Okay. So this is going to be about iterated partial derivatives. I keep using the analogy of coming back to single variable calculus. So when you did single variable calculus, you learned about derivatives, and you learned about second derivatives, right? And second derivatives have cool physical meanings, but today we're going to learn about iterated partial derivatives, meaning basically second derivatives, but since we have partial derivatives with respect to different variables, things get kind of interesting. So let's see, we have, we'll start by looking at scalar valued functions, but as we've seen many times at this point, if you have a vector valued function, you can break down into components, which are the scalar valued parts. And so if we have, we can take these, what we would call second derivatives, right? And this is like an interesting new notation. We have the d squared of f, which is kind of similar to how we did in single variable, but now we have dxi times dxj. And what this is this is the, it's a different color. This is the partial derivative with respect to xi of the partial derivative of f with respect to xj. Okay. Cool. And you can imagine a special case of that is when I and j are the same. So you can have d, that's what this notation is here, which looks more like the notation you're maybe used to for a second derivative in single variable calculus, right? You have d squared f over dx squared, right? Or dy squared, right? Or I guess in single variable is always dx squared, but now we're going to have dx squared, dy squared. If there's more variables, then that's why we have used this notation when there's more variables. But then this is just, again, this is just d dx of df dx, and I should put i's here. Okay. Okay. So some vocabulary. If I is different from j, then this one over here is called a this is called we'd call this a mixed partial because it's mixing two different variables. Okay. So for example, if n equals 2, then we can just think of the xi and xj as just x and y, right? Is that an equal sign? This here is a not equal to sign here. So the equal to with the slash strip. The rest, this here is an equal sign and this here is an equal sign. Okay. So basically, if you have different variables that you're taking the derivative with respect to, if you take the derivative with respect to two different variables, so for example, in n equals 2, if you do dx, ddx, and then ddy, that would be called a mixed partial derivative. Okay. Okay. Cool. And then some additional notation. I think next is we're gonna jump into some examples right away. But some additional notation before that is sometimes instead of writing all of this notation, so for the partial derivative of a function with respect to x, we can write fx, f sub x, okay, and then like similarly with respect to y, if there was you'd get f sub y, or even with z, it would be the same thing. You can imagine like this is a little subscript, so it's not like next to it, it's like in the bottom, you know. And then what this makes nice is that you can think of the iterated derivatives. So dx dy is f sub x y, right? Because it's f sub x sub y, right? So we take the derivative with respect to x, and then we take the derivative with respect to y. Okay. So the confusing, oh, actually, it's actually yx, right? So this is the confusing part. And it even confused me there for a second. But with this notation, we're kind of working from right to left over here. But from this notation, we're working from left to right. Okay. So because if you see this, right, this is by definition, this is the derivative of this stuff in here, right? This is just like a shorthand notation for this, right? And so working from here, because we're applying stuff on the left, it's kind of working from right to left. But over here, we're applying stuff on the bottom right, and so it's going from left to right. Okay, so that's the confusing part, is that the order kind of changes, but this notation is much nicer when you start writing down, especially, you know, I just wrote down second derivatives here, but you can imagine I could then take a derivative of the derivative's derivative, right? So this is the derivative of the derivative. I could take a derivative. I can then take a derivative of this, and that gives me the third derivative and fourth derivative, et cetera, et cetera. And so if we were doing that, we'd be here all day with this notation, but this notation just clears it up right away. It's just the confusing part is that in one of them, you're going from right to left, and the other one, you're going from left to right. I think it helps to like write it out. So like this one, if you write it out like this, it makes sense. Like, okay, I'm doing this derivative first, and then I'm doing this derivative. And this similar here, if you write it out like this, okay, I'm doing the y derivative first, and then I'm doing the x derivative. Okay. Does all of this make sense, the notation there? Okay. Actually, I think there's one more slide before examples, but we're gonna move on here, okay? Cool. Oh no, there isn't. Okay, there's a nice set of examples first. So if we take f of x comma y to be this function here, the sine of x squared y, we can compute, so here it says compute all second partial derivatives of this function. So the first thing I'm going to do is I'm going to compute the first partial derivative with respect to x. So f sub x is equal to this derivative with respect to x. So we have to do a little bit of a chain rule here, right? So first of all, we have cosine of x squared y, but then we have to multiply by the derivative of the inside, which in this case is 2xy, right? And then we can do this derivative of this with respect to y. Actually, I think, no, I think I'll jump to that. F with respect to y is, well, if we take the derivative of this with respect to y, it's very similar. We get cosine of x squared y because we need to take the derivative with respect to the outside first, and then the derivative with respect to the inside is just this x squared. Okay. So now we can take the derivative of this with respect to x or with respect to y. So if we do the derivative of this with respect to x is the derivative is fxx. And so we get here, now there's a product rule that happens here. So it's 2y cosine of x squared y plus 2xy times negative sine of x squared y times 2xy, right? So again, if you're keeping track with all of this, is just some chain rule happening here. I don't want to simplify too much, but there's the not chain rule. There is some chain rule happening here, but the big thing that's happening here is a product rule, right? So this is a function of x, and it's a function of x times a function of x. So it's the derivative of this times this. So that's 2y times cosine of x squared y, plus this times the derivative of this. And then there you have to use another chain rule. So the cosine becomes negative sine, and then you do the derivative of the inside with respect to x, which is 2xy. And so you get something that looks like this. And now similarly, you can take the derivative of this with respect to y. And so this one's also going to need a product rule. So we get 2x cosine of x squared y plus, and now you have 2xy times x squared times negative sine of x squared y. Okay. Cool. Okay. So here's our first two. These are the first two answers because we're looking for the second derivatives. That's these guys here. Oops. Okay. And now we're going to take the derivatives of both of these guys. So we're going to do fyx, or sorry, of this guy with respect to both x and y. So we start with fyx. So take the derivative of this with respect to x. Well, again, that's going to be a product rule. So that's going to be this times, or the derivative of this times this. So 2x cosine of x squared y plus x squared times 2xy negative sine of x squared y. Okay. And last but not least, we can now take the derivative of this with respect to y. But before that, someone's asking about this here. So yeah, this is negative sine of x squared y. Yeah, thanks for asking for that. This is cool. So lastly, we have the derivative of this with respect to y, which I think is the probably the the easiest of the second derivatives because this is no longer a product of functions of y. It's just a function. Only this part's a function of y, and so we just get negative x squared. Maybe I should leave the negative off. So x squared times 2x or times x squared times negative sine of x squared y. Okay, cool. Okay. Any questions on that? I guess I should probably box this. Like I did the other one. So these are our answers. So if it's a function in two variables, then there should be 4 answers, right? Because there's 4 different combinations. You have xx, xy, yx, and yy. And so you can compute those like this. We're going to do the same thing with this problem. These were a little wider than I expected, so I'm just going to do these on a separate page. And we can get started on those. And oops, do that here. And so let me put it back here just for a second so you can copy it down if you didn't yet. And you can totally simplify all of these, right? Like there's a lot of stuff, unsimplified stuff happening here. Like, right, this should be 4x squared y squared. This should be 2x cubed y squared, and then you should probably move the negative sign over here. So it's just a minus instead. But I didn't with that to save some space. Okay. So now here we have this new function g of xy, and we want to compute the partial. Again, we're going to start with just the regular old partial derivatives. Someone's asking if on the quiz you have to simplify. I wouldn't say you have to, but it's probably nicer if you do. Though there's these pros and cons to simplifying. Like the more you simplify, the more room there is for you to make a silly mistake. But if you don't simplify enough, then it's like, okay, maybe like you get a kind of a taste for how you simplify. So for something like this, it would probably be best for you to simplify. It's never going to be like all or nothing. Like if you don't simplify, you don't get any points at all. Like it's at most you'll lose like 1 point or something like that. But even then, I doubt. With again, it also depends on like who's grading. But I probably wouldn't take off any or many points. If like, for example, and the problem like exactly like this exact problem was on a quiz. Someone did this, you'd get full marks because it's clear to me that it's like, okay, you were just writing it down as you did the chain rule, that's fine, or as the product rule, that's fine. But if you simplified it completely, I'd probably be happier, and I mean that's always nice. Okay, so speaking of product rules, this is going to definitely involve a product rule because you have a function of x times a function of x. And so we take the derivative of this with respect to x, we get 3x squared y cubed e to the xy plus, and then we have x cubed y cubed. And then we have the derivative of e to the xy with respect to x. That's y e to the xy. Okay. And in this one, since I'm going to be taking another derivative of it, I think I am going to simplify it a little. We can turn this into 3x. Let's see, how do I want to do this? Yeah, I think I'm going to factor out the e to the xy. And then this becomes 3x squared y cubed plus x cubed to y to the 4th. Oops, should be times. Okay. So this is one of the cases where it's nice to simplify. If it's in the middle of your work, you should probably simplify it because it's going to make the rest of your work easier. Because then we just have to take the derivative of this, which Maybe it doesn't look much easier than this, but when we get to it, I think it's easier because it's only one product rule instead of doing two separate product rules. Okay, and we'll see that in just a second. Okay, so next we're going to go to the partial with respect to y, which if you look at this function, it's actually like it's what we'd call symmetric with respect to x and y, meaning that x, if you reverse the roles of x and y, this function would stay the same. And so this basically just becomes, the derivative becomes the same thing, but with the x's and y's replaced. And so if we do that, we get, so if we just do it by hand, we get 3y squared x cubed e to the xy plus x cubed y cubed x e to the xy, which simplifies, again, we factor out the e to the xy, and we get 3 y squared x cubed plus y cubed x to the fourth. Okay. Okay. Cool. So let's finish up this problem real quick. So let's do g x x. So it's the derivative of this with respect to x. Okay, so that means there's going to be a product rule. So we're going to do so the derivative of this times this, so that's y e to the xy times, and then the rest, this stuff in parentheses stays the same. Plus, now this e to the xy gets left alone, and we just do the derivative of the stuff in here with respect to x, so that's 6xy cubed plus 3x squared y to the fourth. Not too bad. It's kind of long and ugly looking, but it's in terms of the actual work we had to do, it wasn't too bad, right? We had to do a big product rule, but once we actually got down to it, the derivatives themselves weren't bad. Okay. Now gxy is the derivative of this with respect to y, which again, similarly is a product rule. So first we'll do the derivative of this with respect to y. So it's x e to the y times, again, all of this stuff gets left alone. And again, if my handwriting at any point here needs clarification, please feel free to ask. Plus, we leave the e to the xy alone, and now we take the derivative of this stuff with respect to y, which is now 9x squared y squared plus 4x cubed y cubed. Okay, cool. And so these are our first two answers here. Okay. Cool. So now we're going to go down to g of y. And now we're going to take the two derivatives of this function. So g y x is equal to, again, we take the derivative of this with respect to x. Again, it's a product rule. So it's y e to the xy. Yeah, is that right? Times, again, all of that stuff gets left alone. So 3y squared x cubed plus y cubed x to the fourth. Sorry, so same thing, isn't it gyy? No, so this is the derivative with respect to x of the derivative with respect to y. So we're taking the derivative of this with respect to x. So this would be gyx. So it's gy, and then take the derivative of that with respect to x. So gyx. Unless I did something really silly. No, yeah, so this is the derivative of this with respect to x. Treat y like a little coefficient, and so it comes down. Plus, now do it the other way. So exy, take the derivative of this with respect to x. So we get 9x 9x squared, or yeah, so bringing that down to 9y squared x squared plus 4y cubed x cubed. Okay, cool. So that one, it wasn't any harder than these, but for some reason this one, like, this is going to inevitably happen. It's going to, something about it just confused me a little bit and so it slowed me down a little bit, but we got through that. Okay. Does that make sense? Any questions about what I did here? Again, I'm just using a product rule. There's a product here. So I take the derivative of this times, or the derivative of this times this plus this times the derivative of this. Product rule with this and this. U times V, if you will. Okay. And now lastly, we have GYY. So this is the derivative, now the derivative of this with respect to y. So this gives us x e to the xy times, again, don't touch that. Plus, we don't touch the e to the xy, and then take the derivative of this stuff with respect to y. So now it becomes 6yx cubed plus 3y squared x to the 4th. Okay. And we can call it a day there. Okay. Cool. Any questions on that? So someone's asking, so it doesn't actually matter what order you do these in, you just do have to do the first derivatives. Like I could have done these in the opposite order and then these in the opposite order. Doesn't matter. There's some rhyme or reason to the order I'm doing this, but it's maybe not super obvious. It might make more sense to do like gxx then gyxy and then do gyy and then gyx to you. If the order you do these, it doesn't matter as long as you do the first derivative. Like you need to do this before you can do either of these, and you need to do this before you can do either of these. So the order I have them here is acceptable, but you know, there's no correct order to do them in. Cool. Any other questions? So there's something maybe you noticed about both of these examples. It's more clear in this one. So let's look at this. This here, this mixed partial and this mixed partial. What do you notice about those? Yeah, they're the same. So in this one, fxy equals fyx. So this one, it almost looks like, oh, well, but that doesn't work here, right? It almost looks like you got different things here. But first of all, I have a silly typo up here. There should be an X there. But second of all, it's even if I fix that typo, it's not completely clear that I've gotten the same thing. Like this term and this term look the same. Okay, that's fair. But this term looks very different from this term. There's a Y there and an X there. Maybe we messed up or something. I don't know. But nope, it's the fact that we can factor an X out of here and then distribute this Y back through, and we get the exact same thing here and here. So if you algebraically manipulate this one, you can make it look like this one. And so, or vice versa. And so these two are also the same in this situation. And so it's actually going to be the case that that's actually always going to be the case. And I think that's the next slide. Okay, so it's not the next slide, but it's an upcoming slide. So we're going to talk about that. Okay. But before that, I want to introduce a little bit of vocab. And that's basically, so you might see something called continuously differentiable. It comes up in the homework, or C1, C with the superscript 1, C to the power of 1. Capital C. And they use that to describe a type of function. And what that means is just that all of the partial derivatives exist, and they're all continuous functions themselves. And so you call it a C1 function. And you can generalize this to mean, you can generalize this to a C2 function if all second derivatives exist and are continuous. We say F is C2 or twice continuously differentiable. So maybe continuously differentiable is a little bit confusing. It almost sounds like differentiable. It almost sounds like you can continuously differentiate it. Like you can do it at all. You can keep doing it. Like you can do it continuously. But what it really means is that you can do it everywhere in like what we call a continuous fashion. In other words, the derivative is continuous as a function itself. Okay. Okay, so just a little bit of vocab. It comes up in the homework. This is more of a conceptual thing, so there's not really any problems I can do with this. But when it comes up on the homework, you might be like, "What does that mean? Why do they keep mentioning? Why do they keep saying it's like twice continuously differentiable, or C2? What does all that mean?" And you could also, like, if you wanted to, you could say the same thing about third derivatives, all of them existing and being continuous. That's 3 times continuously differentiable, or C3. You can do Cn if you want to say that, or C to any power, and it's just that you can take that many derivatives. And then there's also something called C infinity, which just means you can take derivatives as many times as you want, which is probably the most common type of function we'll see. Okay, cool. Just a little vocab there. But then going back to the last point that we looked at when we were looking at those examples, that's what's going to come up on the next slide. I'll pause here for you guys to be able to write this down, this vocab down if you're writing that down. But just also remember that I'll post the notes later. So if you don't get it all down right away, it's fine. But going back to those examples, what we noticed, right? It's still in the chat there. Someone mentioned it, is that if I take the mixed partial derivatives, so if I take f of x and then if I take the derivative of f with respect to x and then I take its derivative with respect to y, in those examples I got the same thing if I took the derivative with respect to y and then took the derivative with respect to x. And so that's what we call this, like what we call the law of mixed partials sometimes, but I just think of it as, hey, mixed partials are always going to be equal. So f here is a function from Rn to R, so it's a scalar valued function in several variables, and it's C2, so it's twice continuously differentiable. Okay, and so we get this equality. So sometimes you'll see this written as the way you guys have it in the chat. So f of xy is equal to f of yx, but it doesn't have to be x's and y's. It can be like zx is equal to f of xz, or f of yz is equal to f of zy, right? And so mixing partials is always going to give us the same answer. So the picture so what should be picturing here is in a scaled up version, basically what's happening here is in the domain, so in the domain, what you have is your dx, which you can think of as almost like a delta x, and then over here you have delta y. So if you do this and then delta y, well, that's going to put you up here. But then if you do delta y and then you do delta x, that puts you in the same place, right? So if you like thinking in terms of delta, like if you remember in calculus, the d symbol is like basically means an infinitesimally small delta, right? And that's how we kind of teach you to picture what this notation is trying to tell you. And what's happening is that at the infinitesimal level, this is what's happening in your mixed partials. So you're going like this, and then you're doing like this and this, and you're measuring the rate of change going from here to here in both of these paths, taking both of these paths. Okay. And so of course, if you take both of these paths, you're going to start at the same place and end at the same place. And so the rate of change is going to be the same. The average rate of change, I guess, over these is going to be the same. Cool. Does that make sense? This is kind of the picture that I have going on in my head. And now this makes some computations kind of easier. Now, I will say that there's some problems on the homework that are like, confirm the law of mixed partials, or confirm this theorem, which is just the theorem that states this, for this function. And on online homework, it's kind of silly because most people are just going to compute this mixed partial once, and then it should be the same for both answers. But like on a quiz, what you'd be expected to do, somewhere where you're showing work, or a worksheet, I guess would also be one of these cases, is you want to, if we're asking you to like, if you're ever asked to like confirm that this is true, right? What you're really asking to do is like compute this, the by definition, and then compute this by definition, which is two different computations, two different workflows, and then make sure that the final answer you get in either case is the same. Okay. Because like here you take the derivative with respect to xj and then take the derivative with respect to xi, and over here it'd be the opposite, take the derivative with respect to I and then with respect to xj. So in the work, it's different for computing both of these, but the answer you get is the same. And so that's what it's asking for you to, when it asks you to confirm that this is true. Okay, so compute it both ways and make sure you get the same thing. Cool. But there's this other type of problem where basically once we know that this is true for all C2 functions, what we get is this. I think it's kind of a neat kind of problem, because at first it seems like it should be harder, but then once you have this law of mixed partials, it's actually not too bad. Okay. So what we get is a question like this. So we get asked, is there a function from R2 to R such that this is equal, such that the partial derivative with respect to x is equal to this, and the partial derivative with respect to y is equal to this. Okay, and I should throw in, is there a C2 function? But if there's a function, then it's going to be C2. Well, yeah, I should say C2. Okay, and the question is, does there exist a C2 function with this partial with respect to x and this partial with respect to y? Okay. So how do we do this? At first, it's like, well, how am I supposed to do? I like take an antiderivative or something? Does that how you? And I've seen people try to do that, and it's like maybe that there's like a way to make that work. But what this is trying to get you to use is this law of mixed partials. You should remember that if this function did exist, so maybe I'll start writing things down. So I'll say it as, if such a function did exist, then because of the previous slide, f of xy should equal f of yx. Sorry, f sub xy should equal f sub yx, right? So taking these mixed partials should work. So if we were able to find a function, then this should have this property. So let's check this out. Let's see what f of xy is. Well, f of xy is take the derivative of this with respect to y, so that's 3x squared. And then fyx, well, that's the derivative of this with respect to x, which is 3y squared. So we actually got something different here. So we got fxy is not equal to fyx. So this function, so I'll write it in the fancy way, no such function exists. Okay. Cool. Any questions? So there are questions like this on the online homework, which is like, does a function exist with I think the homework phrases it is, could a function exist with these two things? And then you just compute the mixed partials based on this, because it gives you like the first step of the two mixed partials. Take the next step, so compute this with respect to y, this with respect to x, and then you get different things. So the answer is no, or if you get the same thing, then the answer is yes.